Hello, friends! Welcome to today's cosmic journey, where we'll uncover the extraordinary story of how scientists determine the age of our universe, from the fiery birth of the Big Bang to the present moment. If you love a blend of detective work with cutting-edge technology and mind-blowing astronomical discoveries, don't forget to like, subscribe, and share this video with anyone who dreams of exploring the heavens. Understanding how long it's been since the universe went from an unimaginably hot, dense state to the vast, magnificent expanse we see today is fundamental to grasping cosmic evolution. By comparing the age of star clusters and galaxies with the universe's overall lifespan, researchers can piece together the timeline of star formation, the creation of heavy elements, and the emergence of planets, and ultimately, life itself. Every new, ever more precise measurement adds another tile to this grand mosaic of cosmic history. Our story begins in the early 20th century, when astronomers noticed that light from distant galaxies appeared shifted toward the red end of the spectrum. This redshift signaled that galaxies were moving away from us, and that the farther a galaxy lay, the faster it receded. Asking when did this expansion begin led to the first rough estimate of only a few billion years. Today, this seems like a dramatic underestimation, but at the time it reflected the limitations of telescopes and distance measurements. To overcome these uncertainties, scientists developed what we call the cosmic distance ladder. Its first rung is parallax, measuring the apparent shift in position of nearby stars against the background as Earth orbits the Sun. The larger the shift, the closer the star. With parallax, astronomers could nail down distances to the nearest stars with impressive accuracy, creating a solid foundation for more distant measurements. The next rung up the ladder features Cepheid variable stars. These pulsating stars brighten and dim in a regular cycle, and the length of that cycle directly correlates with their true luminosity. By comparing a Cepheid's known brightness to how bright it appears from Earth, astronomers calculate its distance, sometimes reaching hundreds of millions of light years. Thanks to Cepheids, estimates for the universe's age climbed into the realm of 10 to 20 billion years. Then came one of the biggest leaps, type Ia supernovae. In binary star systems, a white dwarf steadily steals material from its companion until it reaches a critical mass and detonates in a spectacular, standardized explosion. Because every type Ia supernova shines with nearly the same peak brightness, these cosmic fireworks serve as reliable, standard candles. Observing how bright they appear from Earth lets scientists compute their distance, and from that, derive the expansion rate of space itself. Analyzing dozens of these explosions honed age estimates to around 15 billion years. Yet the revolution truly arrived with the cosmic microwave background, the universe's oldest photograph. Roughly 300,000 years after the Big Bang, the cosmos cooled enough for atoms to form and photons to travel freely. The WMAP satellite first mapped tiny temperature fluctuations in this relic radiation during the first decade of the 21st century. Not long after, the Planck mission refined these measurements to astonishing precision, detecting variations smaller than a millionth of a degree. By modeling these subtle ripples, scientists determined the proportions of ordinary matter, and dark energy, leading to an age estimate near 14 billion years. To bolster confidence, researchers turned to baryon acoustic oscillations, regular wave patterns imprinted in the large-scale distribution of galaxies. These patterns are fossils of pressure waves rippling through the hot plasma of the early universe. Measuring the separation of these galaxy clusters at different distances provides an independent yardstick for cosmic expansion. Matched with supernova and microwave background data, baryon acoustic oscillations reinforce our view of a universe about 14 billion years old. Another powerful tool is gravitational lensing. Massive galaxy clusters warp the fabric of space-time, bending light from more distant objects into arcs and distorted images. By analyzing how severely light is deflected, astronomers map the invisible dark matter and cross-check other distance measurements. This lensing effect serves as yet another independent test, tightening the screws on any lingering uncertainties. Today, all these observations merge into a comprehensive framework known as the Lambda Cold Dark Matter Model, or LCDM for short. This standard cosmological model blends microwave background measurements, type Ia supernovae, baryon acoustic oscillations, and gravitational lensing into a consistent narrative describing the universe's evolution from its first moments to its current accelerated expansion. The synergy of these methods drives uncertainties down and delivers a rock-solid age for our cosmos. Despite this incredible precision, a curious discrepancy has emerged, often called the Hubble tension. Estimates of the universe's expansion rate derived from the cosmic microwave background yield a slightly slower pace than those based on supernovae and gravitational lensing. The gap is subtle but significant, hinting that our standard model might be missing a vital piece, perhaps a dynamic form of dark energy, an unknown variety of dark matter, or new physics in the universe's earliest moments. On the horizon stand two groundbreaking missions poised to crack this mystery. The European Space Agency's Euclid telescope will map billions of galaxies in 3 dimensions, probing how dark energy shapes cosmic structure. Meanwhile, the James Webb Space Telescope peers deep into the infrared, capturing the first stars and galaxies that formed after the Big Bang. Combining data from Euclid and Webb could finally resolve the Hubble tension or unveil entirely new cosmic phenomena. But you don't have to be a professional astronomer to contribute. Even a modest backyard telescope lets you track variable stars and supernovae in nearby galaxies. By logging your observations and sharing them on citizen science platforms like Zooniverse, you provide the vital extra data scientists need to refine the cosmic distance ladder. Your passion fuels every new discovery. It's astonishing how far we've come in just over a century. From crude estimates of a few billion years to pinpointing an age of roughly 14 billion years within a fraction of a billion, we've witnessed a true golden age of cosmology. Whether the Hubble tension uncovers new physics or ultimately bows to refined measurements, we stand on the brink of discoveries that will reshape our grasp of time and space. If this journey through cosmic history has sparked your curiosity, drop your questions and topic ideas in the comments. Want to learn more about dark energy, dark matter, or the latest Webb images? Let us know! And don't forget to like, subscribe, and share. Your support lights the path for our next astronomical adventures.